Okay, so today we are going to have the chapter 4, and as I teach the previous chapter, we only consider the conditions for the hydrostatic. But start from this chapter, we are moved to the kinematic problems for the fluid. Okay, so when we talk about the kinematic, so the most important thing we are trying to describe the fluid flow velocity field. Okay, so the first important thing in this chapter is the flow field. And because the topic is related to kinematic properties, so as you can see, there are some properties we related to the kinematic problems. The first one is the motion of the fluid particle, and the second is the velocity, and the final one is the acceleration. Okay, so for class today, we are looking for the motion and the velocity. And then next week, we will move to discuss with the acceleration properties of the fluid. And then there are some flow conditions, as I showing here, the steady, uniform, laminar, turbulent, and inviscid. Okay, so today I will describe all of the flow conditions showing here, and why I can say that the flow is steady state, or the flow velocity is uniform, or I can say the flow is the turbulent flow. So I will provide the certain mathematic representation to describe the flow condition. And there are three lines: string lines, path line, and the strike lines. The lines showing here, we are trying to describe the fluid motions. So the different lines have the different definitions, and I will teach in later. Okay? So this is the outcomes for these chapters. So first we describe the flow, and based on the different methods, what the method I mean here, we have the string line, strike line, and the path line. Under three type lines showing here, can we describe the flow? Okay, and to approach Eulerians and Lagranges, two approach will help us to describe the flow. And some kinematic properties, as I mentioned before, we are focused on the velocity and the motions. And then next week, we will focus on the accelerations for the fluid particle. And the two important equations we'll teach in this chapter. First one is Euler's equation, and the second one is the Bernoulli equation. And since we already know how can we understand the Bernoulli equations, and then we will apply above equation to measure the fluid velocity. Okay, so we have some exercise. If we apply the Bernoulli equations, and then how can we measure the flow velocity? Okay, and before, all of the flow are linear flow. So the final chapter we are moved to, if we discuss the flow, is the rotational flow. So we will have the different problems if the flow start to rotate, and how can we apply the Bernoulli equations for the rotational flow. Okay, so this is very quickly I introduce the outcomes for these chapters. Okay, so we move to describe three lines will help us to describe the flow, fluid flow. So the first one is very important. We call that the string line. And the definition for the string line, the line is tangent to the local velocity factor. This is the definitions for a string line. That indicate if I have a string line like this shape, this is my string line, and I pick out the one point, maybe this is a local point, and then this local point, the velocity factors will along these directions. So this is my velocity factors. So let's indicate if I plot the tangent lines cross over this point, this is the tangent line will parallel to the local velocity factors. So I can find out the many local points, and I plot many tangent lines, and I connect all of the black points, and then define the line, right? And the red line, we call that the string line. So every string line are tangents to the local velocity factors. Okay, so I can have the different tangent lines at a different location, but each tangent line will parallel each other. Each tangent line will parallel to each other. So the mathematical definition for a string line, we always say that the spatial gradients are always equal to the velocity gradient. This is certain definitions because the tangent directions of the line is parallel to the velocity factor. That indicates the spatial gradient will be equal to the velocity gradient. Okay, so you see the mathematical definition in here. The left-hand side showing here. Okay, this is the spatial gradient, right? The x, the y, the ratios. And the right-hand side, I use the v and the u. What is the v? V is the fluid velocity along the y directions. U is the fluid velocity along the x directions. Okay, so that's why I say that the ratio between the velocity is equal to the spatial ratio. Okay, so this is a definition, very important definition for the string line. And then later we will have the exercise, so we can compute how can we define the string line by ourselves. And then the second, we call that the strike line. Okay, and then the final one is the path line. So we have the cartoon figures to describe how difference between the path line and the strike line. Okay, so you see here we have the blue arrows. This is a string line directions when the time is less than t0. Okay, and another direction for the string line is maybe the horizontal. I call this the east component, and there's the north component. I define the directions, the east direction and the north directions. So the north directions, we have a different time point. If the time less than t0, the string line direction is going to east. If the time is larger than t0, and the string line is going to the north directions. So actually we know that the flow direction will change when the time is less than t0 and the time greater than t0. Okay, so we have two different string line directions. Okay, and the black dot showing here, the dot showing here, okay, And the dot showing here is indicate the time is less than t0. And because the straight line is go to the east. So the black dot will move to the right hand side when the time increase, right? And when the t is larger than t0, so the straight line is going to the north. The straight line is going to the north. So you see the dot, the black dot showing here will change the directions and move to the north. If you connect all of the black points showing here, and we say that is the path line. So the path line is very easy to understand. We just check the fluid particle at the different time point. And we connect all of the fluid particle at a different time point. And the line, we call that the path line. OK? 那这个我们就叫轨迹线嘛，因为我们从头到尾就追着它跑嘛。So it is similar to we find out the typhoon, and we check the typhoon at the different time point. And then finally, we can provide the path of the typhoon. Okay? So how different compared to the strike line? Okay, again, so you can see this is the strike line at the t equal to t0. So we have the one strike line, that's the black line showing here. This is a strike line at the time point, the t0. And when the t0 is larger than t is larger than t0, so we have a different condition. We have a different condition in time point in here, but you see the strike line is go the north first and then move to the east. Okay. So how difference? The difference is this part. But for the strike line, they are different, right? So the strike line is only related to the time point. Like the smoking, maybe the smoking air initially just going up, but we have some typhoon coming, so the smoking will move to another directions. It's rely on the different the wind direction, right? So the wind direction just going here, so the smoking will move to another way. Okay, so the strike line is only related on the different time point. Currently all of the fluid particle at a certain time, and I connect all of the particle together to make the strike line. OK， 所以 strike line 就是我在现在这个时间点，所有从我出发的烟，那它现在所有的连线长怎么样子？那10分钟以后，这些烟不是会走掉吗？那10分钟以后，从我出发所有的烟再连起来，那它长怎么样子？那跟 path line 不一样 ，path line 是我从头到尾都追着同一颗东西在走，这颗球跑到哪里我就追到哪里，所以我的连线就是这颗球的轨迹，这个叫 path line。那 strike line 是所有通过我的指点，在不同的时间点的连线，所以这些烟都从我的鼻子吐出来的话，那10分钟这些烟在这里嘛，再过10分钟这个烟可能就跑到教室的后面去了。所以我的 strike line 会是一个很长的一条线。Okay, so the difference is the path line just fix one point, and track the point at a different time point. But the strike line, I fix the one point, and the smoking air will go through this point at a different time point, and I just connect all of the points go through the one point, and at a different time, so the strike line will have a different shape. strike line will have a different shape. Okay, so usually we only, for the fluid problem, we only focus on 2 lines. The first one is the string line, and the second one we use the path line. Sometimes we don't use the strike line, depend on different problems. Okay, so so right now we are moved to describe the different flow conditions. So the first one we call that how different they are. The first one is we call that the steady, and what are the unsteady. So you call that the mathematical representation here. The V is our velocity. The V is our velocity. So we have the velocity and the dv dt. That means the velocity will be changed with the time. But the differential, final differential is equal to 0. That means the velocity didn't change with the time changes. Okay? In that case, we call that the steady. But if the velocity differential with the time is not equal to 0, that indicates this flow condition, we call that unsteady. Okay, so sometimes you see that the steady and unsteady, that indicate the physical properties will change with the time or not. If the physical property didn't change with the time, and we call that the steady. Okay, so this is figures we describe what is the string lines. So the blue line showing here, they are the string line. They are the string line. They are the string line. And the right hand side, the blue curves, they are the string line. They are the string line. And the one important point showing here, we call that the stagnation point. Usually we call that the 停滞点. And in the following material, I will teach you what's happened in stagnation point. Okay, so in the features, we will discuss if at this point, how large the velocity we have, and what the pressures at these locations. Stagnation is a very important point for our fluid problems. So in this chapter, I will answer you at this point how large the velocity in here, and how large the pressure at this point. Okay, so in the following chapter, I will teach you. So before our purpose in this chapter, first we will have the fluid velocity field. And if we have the velocity field, how can we determine the string line function? If we have the velocity field, how can we determine the string line functions? Okay, in the example showing here, I directly plot the string line, and you can see the answers. But how can we determine the string line, like this shape? So this is a very important purpose for these chapters. So the first one, we trying to describe the velocity field. How can we determine the velocity field? So it's a cartoon figure showing here. First we will define the reference point. And if we would like to determine the fluid particle A in here, this is a fluid point particle A. And we just find out the factors of the displacement change with the time. And we can define the velocity at the A point. But the A distance is the factor. So when we determine the velocity, what do we need? We need the magnitude of the velocity. And then we need the directions of the velocity. Okay, so we need the two informations the velocity is a factor, not the scalar. Okay, so we need to determine for these questions, how can we determine how large the velocity magnitude and what is the velocity directions? As you can see, the different points of the fluid particle, the velocity factor has the same magnitude but with the different directions. Okay, so for the velocity field, two information we need to determine. The first one is the magnitude of the velocity, and the second one is the directions. Okay, so usually, this is our velocity field. This is the factor. This is the factors. And we are looking for the three-dimensional velocity field. So we have the I, J, K unit factors. And then for each factors, for I is x directions, and we use the U. We use the U symbol to describe the velocity along the x directions. And we use the V indicate the velocity along the y directions. And we use the W indicate the velocity along the z directions. So usually we will have the U, V, W. That's indicate the three-dimensional velocity directions along the x, y, and z. And each velocity scalar, we have the x as function of the x, y, z, and the t. X, y, z, and t. X, y, z, and t. That means different location and a different time point, we will have a different velocity magnitude. Okay, and at a different time point and different location, we will have a different velocity direction. The velocity direction depends on the UVW. Okay, because the UVW indicates the x, y, z direction velocity respectively. Okay, so and sometimes if our straight line is not a linear line, it's the curvature line. If the curvature line, this is our straight line. And then we can distinguish the velocity to the tangent directions and the normal directions. Okay, if the straight line not the linear line, it's a curvature line, so we can distinguish the velocity unit to the tangent directions and the normal directions. Okay, so this is very simple ideas and example to figure out how can we describe the velocity field. So as I already write down the equation showing here, and this is the velocity factor, so we have the directions. The directions only along the I directions. Okay, I is x directions. And we know that the U will equal to 3x plus the 2y. And because there is no time information, right? There is no time information. So that means the flow for this case is steady, right? Because the velocity didn't change with the time. The function in showing here, there is no time operation, right? There is no time operator. So we will call that the flow. First one, this is the steady flow. Because there is no any time variable in our velocity functions. So we don't have the time variable. And the second, because there is only one direction, right? It's I directions. So this is a one-dimensional velocity field. Because the direction only have the one. And then this direction is along the I directions. So we are only focused the x direction velocity field. So right now we can pick up the answer. The velocity field in this case, we can call that the 1D velocity field along the x directions. So the 1D, 2D, or 3-dimensional only depend on the I and the J and K. In here, we only have the I, so this is the 1D velocity field. But you may confuse things because there are some x and y showing here. But the x and y only define how large velocity magnitudes along the x direction at this point, right? So you can see the arrow showing here. If the x increase, the velocity magnitude will increase, right? That's because 3 times of the x. If the y increase, and then we can see the velocity also increase. That's because the 2 times of the y. So the velocity as function of the x, y is only control the different point have the different velocity magnitude. That didn't mean it's a 2-dimensional flow. The dimensional flow only depend on the I, J, and K. In this case, we only have the I factors. So that means only 1-dimensional velocity field. Okay, and if you connection all of the velocity, local velocity factors, that's our straight line. So we know that the straight line is the horizontal line and with the x directions. Okay, so maybe I stop here and we just move to introduce our quiz today. 好，那大家是不是